Welcome to this lecture on the Michaelis-Menten equation. Today we are going to explore the absolute foundation of enzyme kinetics. We will build this concept from the ground up, starting with a simple, intuitive analogy, moving through the mathematical derivation, and finally understanding how this applies to real-world biochemistry and pharmacology. By the end of this video, you will not just memorize the equation, but you will truly understand where it comes from and what it means. To begin our journey, let us start by imagining a busy pizza kitchen. Think of the chefs as our enzymes, and the raw pizza dough as the substrate. If there is only a little dough, the chefs are mostly waiting around, so the rate of making pizzas is slow. As you bring in more dough, the chefs work faster. But eventually, if you dump a massive mountain of dough into the kitchen, the chefs will be working at their absolute maximum speed. Adding even more dough will not make pizzas come out any faster, because every single chef is already 100% busy. This concept of reaching a maximum speed is called saturation, and it is exactly how enzymes behave in our bodies. Now that we understand the idea of saturation intuitively, let us look at the formal definition. The Michaelis-Menten model is a mathematical way to describe how the initial rate of a reaction changes depending on the amount of substrate present. It assumes an enzyme binds to a substrate to form a temporary complex, which then breaks down to release the product. Why do we care so much about this? In the real world, this is the absolute foundation of pharmacology and medicine. When scientists design a new drug, like a cholesterol-lowering statin, they use this exact model to predict how the drug will affect enzyme speeds in the human liver. It even helps diagnose diseases at a microscopic level. This brings us to the mathematical heart of our topic, the Michaelis-Menten equation itself. Conceptually, this formula bridges the gap between microscopic molecular events and the macroscopic speeds we can actually measure in a laboratory. Let us break down every symbol. V0 represents the initial reaction velocity, which is how fast the reaction starts. Vmax is the absolute maximum possible velocity when the enzyme is fully saturated, just like our busy pizza chefs. The letter S in brackets stands for the concentration of the substrate. Finally, Km is the Michaelis constant, a unique fingerprint for how tightly the enzyme binds to the substrate. If you increase the substrate concentration, the velocity increases. But as the substrate gets infinitely large, the velocity perfectly levels off at Vmax. Before we dive into the complex derivation, let us see this formula in action with a concrete example. Suppose you are studying an enzyme that breaks down milk sugar. We are given a maximum velocity of 120 micromoles per minute, a Michaelis constant of 5 millimolar, and a substrate concentration of 15 millimolar. We are asked to find the initial reaction velocity. We chose the Michaelis-Menten equation because it directly connects these variables. First, we substitute our known numbers into the formula. In the numerator, multiplying 120 by 15 gives us 1800. In the denominator, adding 5 and 15 gives 20. Dividing these gives a final answer of 90 micromoles per minute. Physically, this means the enzyme is operating at exactly 75% of its absolute maximum capacity. Now that we have successfully used the formula, let us understand exactly where it comes from by deriving it step by step. This first chunk of the proof sets up our basic chemical reaction scheme. We start with a free enzyme, E, and a substrate, S. They bind together to form a temporary enzyme-substrate complex called ES. This step is reversible, meaning it can fall apart. The complex then moves forward to create the final product, P, releasing the free enzyme. We assign rate constants to track the speed of each step. K1 is the forward speed, K-1 is the reverse speed, and K2 is the catalytic speed. This creates a mathematical vocabulary to track where molecules are going at any given millisecond, setting the stage for our next crucial assumption. With our reaction scheme defined, this brings us to the most brilliant part of the derivation, the steady-state assumption. Proposed by scientists Briggs and Haldane, this chunk of the proof establishes that shortly after the reaction starts, the amount of the enzyme-substrate complex remains completely constant. Intuitively, this means the speed at which the complex is being built is exactly equal to the speed at which it is being broken down. Mathematically, we write this by setting the rate of formation, which depends on free enzyme and substrate, equal to the rate of breakdown, which can go backward to starting materials or forward to the product. This delicate balance between creation and destruction is the mathematical anchor that makes the rest of our derivation possible. Having established our steady-state balance, we run into a small practical problem. It is very hard to measure the amount of free enzyme floating around in a test tube. However, we always know the total amount of enzyme we put into the tube at the very beginning. So in this step, we use a simple accounting trick called enzyme conservation. The total enzyme is simply the sum of the free enzyme and the enzyme currently bound to the substrate. By rearranging this simple addition formula, we can express the unmeasurable free enzyme in terms of total enzyme minus bound enzyme. We will substitute this into our steady-state equation next. This is a classic algebraic strategy used in chemistry to eliminate intermediate variables we cannot easily measure. Now we take that substitution for the free enzyme and plug it into our steady-state equation. The goal of this chunk of the proof is to isolate the enzyme-substrate complex on one side of the equation, because the overall speed of making the product depends directly on how much of this complex exists. After expanding the terms and doing some algebraic rearrangement, we end up with a messy fraction of rate constants in the denominator. Because writing this out every time is tedious, scientists grouped these constants together and defined them as a brand new term called the Michaelis constant, or Km. Grouping these constants not only cleans up the algebra beautifully, but it also reveals a deeper physical truth about how tightly the enzyme binds to the substrate, leading us directly to our final result. We are finally ready to bring everything together and write the actual Michaelis-Menten equation. In this final step, we connect our microscopic concentrations to macroscopic speeds. We know that the initial velocity of the reaction is determined by the catalytic step, meaning velocity equals K2 times the enzyme-substrate complex. We also know that the absolute maximum velocity occurs when every single enzyme molecule is bound to a substrate. By multiplying our previous equation by the catalytic rate constant, we can substitute these two velocity definitions directly into the math. This elegant substitution bridges the gap between the microscopic rate constants we cannot see and the macroscopic velocities we can measure in the lab, giving us the famous final formula we used earlier. So we have proven that the Michaelis-Menten equation holds true, and we introduced this term Km. This brings us to an important question. What exactly is the physical meaning of the Michaelis constant? Beyond just being a collection of rate constants, Km is a unique fingerprint for every single enzyme-substrate pair. It tells us about affinity, which is how tightly the enzyme grabs onto its target. A small value for this constant means the enzyme grabs the substrate very tightly, requiring only a tiny amount of material to get working. A large value means the binding is quite weak. Understanding this is crucial because it allows biochemists to compare the efficiency of different enzymes directly, which is vital when designing drugs that need to target specific metabolic pathways. To truly grasp the power of the Michaelis constant, let us look at a very famous theoretical example. A student asks, what exactly is the substrate concentration when the enzyme is working at exactly half of its maximum speed? We are given that the initial velocity is equal to Vmax divided by 2, and we are asked to find the substrate concentration. We start by taking the standard Michaelis-Menten equation and replacing the velocity term on the left side with Vmax over 2. Immediately, we see that the maximum velocity term appears in the numerator on both sides, so we can cancel it out completely. This leaves a simple fraction. We cross-multiply to flatten the equation out and subtract the substrate concentration from both sides. Our final answer reveals a beautifully simple relationship. Km is exactly equal to the substrate concentration at half maximum velocity. Now that we have calculated this relationship mathematically, let us visualize it on a graph. What you are looking at is the classic Michaelis-Menten kinetics curve. On the horizontal axis, we have the substrate concentration, and on the vertical axis, we have the initial reaction velocity. Notice how the solid curve starts at 0 and rises steeply. This is our pizza kitchen getting more dough. Eventually, the curve levels off and approaches a horizontal dashed line at the top. That ceiling is Vmax, the absolute maximum speed, where the enzyme is fully saturated. Now, look halfway up the vertical axis, at Vmax over 2. If you follow the dashed line from that halfway point over to the curve, and then drop straight down to the horizontal axis, you hit exactly Km. This diagram visually proves what we just calculated. The Michaelis constant is the exact substrate concentration needed to reach half of the maximum velocity. We have covered a lot of ground today, so let us summarize the key takeaways. First, the Michaelis-Menten equation is the fundamental mathematical language of enzyme kinetics, beautifully connecting microscopic molecular events to macroscopic speeds we can measure. Second, remember that the entire derivation relies on the steady-state assumption, where the creation and destruction of the enzyme-substrate complex are perfectly balanced. Third, Vmax is the absolute speed limit of the enzyme when fully saturated, while Km tells us the exact substrate concentration needed to reach half of that maximum speed. You have now walked through the full derivation and seen how these concepts connect. Mastering this equation means you now have the tools to understand how every enzyme in the human body responds to its environment. Great job!